Good morning, everyone. Today I'd like to talk about instantaneous mass discharge, a new phrase to describe dissolved constituent mass loading in alpine streams. Mass transport of dissolved constituents in stream systems has been described as mass loading or dissolved constituent load. The term mass load has been historically used by the civil engineering field as a design parameter for wastewater treatment plants. For example, sustained peak mass load of biological oxygen demand is a key design parameter for treatment of wastewater. This term load is typically applied as a fixed or steady state design parameter. The term load has been used inconsistently to represent different meanings. For some definitions, load is discharge multiplied by concentration, where discharge is represented by Q and concentration by C. Dissolved constituent is a filtered sample. Total constituent is an unfiltered sample, as in dissolved copper or total copper. Numerous synoptic watershed studies have been conducted typically during low flow conditions, some sites during high flow. Stream flow discharges are estimated, samples are collected, and calculations are made to determine constituent mass loading. Stream profiles and loading spreadsheets are frequently presented as though the samples were collected in steady state conditions. These synoptic data might then be used to calculate a single mass loading value for a constituent to represent a watershed for the entire year, for example, the total maximum daily load program. Water quality standards and regulations are then developed from annualized data that are not representative of the watershed. In alpine stream systems, however, discharges from streams, springs, and mines fluctuates constantly, responding to precipitation, snowmelt, evaporation, transpiration, freezing, and thawing. And dissolved constituent concentrations also fluctuate constantly due to mineral oxidation and reduction, dissolution, precipitation, and non-conservative constituent behavior. Alpine hydrologic systems are constantly changing, but seasonal patterns are somewhat predictable. This top graph shows the Animas River below Silverton, A72. Daily mean stream flow, discharge in cubic feet per second, showing these seasons. Winter low flow, snowmelt runoff period, and the monsoonal rain season. On the lower left here is the Animas River below Silverton, showing the diurnal or daily stream flow discharge fluctuations. You can see how the discharge fluctuates just in a one-day period, in some cases during the spring, increasing as much as 1,000 CFS during the diurnal. That's a big diurnal. Springs and mines also have seasonalities. For example, discharge from the North Star mine, the low flow might occur in February. The high flow might occur during July or August, a full month and a half after the peak flow of the surface water. And so what if you're doing a synoptic sampling study and you have teams of people coming from all over the place, and you go out in the field and you collect a sample, and other people are up basin collecting samples at different times of the day, and then you stay overnight in the motel, and then you're out the next day collecting samples and during the diurnal fluctuations that are occurring, and then you take the data back to the office, get the laboratory results, and tabulate these data as though they were collected during a steady state condition, when in fact they were not. So I have a new phrase to introduce called instantaneous mass discharge. IMD represents the volume mass rate of change of dissolved or total constituent that flows through a given cross-section of the stream channel. IMD changes constantly. IMD is not a fixed or steady state value. The advantage of IMD is to illustrate the true nature of constituent mass loading in alpine streams. We'll use statistical correlations and regression models to exhibit the non-steady nature of alpine streams. And IMD can be used to develop seasonal water quality standards. IMD is the sum of the discharge across the channel, the instantaneous discharge, multiplied by the concentration, where this is a momentary or meantime constituent concentration, and we'll go over that here in a little later. I prefer that the units remain consistent throughout the calculations. For example, if you're measuring discharge in cubic feet per second and your laboratory results are in micrograms per liter, the IMD is represented as micrograms per second. So this idea comes with the help of a friend and discussions about what it means, but this idea comes from the USGS, where instantaneous discharge is measured in the field. In the USGS manual, instantaneous discharge is existing or measured at a particular instant. And so we start with the pygmy meter or flow anemometer. It's at the bottom of this weighting rod with the tagline tape going across the channel. And here I am measuring instantaneous velocity. And I'm measuring the instantaneous velocity of this representative rectangle as you go across the channel. And the instantaneous discharge is a summation of these instantaneous velocities times the area. And the discharge of the channel is the summation of these little rectangles as you go across the stream. A water quality sample is a momentary or mean time sample. A momentary grab is recorded to the minute. A width integrated mean time sample is the best, where you have a DH81 handheld sampler with a Venturi nozzle on it and a 3-liter bottle, and you wade across the stream, collecting a width and depth integration as you go across the stream, and this essentially averages the entire stream section within the 3-liter bottle. The discharge is summarized in cubic feet per second. The width integrated mean time sample, which is averaged within the sample bottle, is expressed in micrograms per liter. IMD results in micrograms per second. And think about micrograms per second coming across this stream section. Extrapolation of instantaneous measurements to daily or yearly values, in my opinion, is a gross misrepresentation of the actual data. For examples, here's two distinctly different watersheds, Upper Mineral Creek and East Mancos River. Mineral Creek at Burrow Bridge, here's model stream flow based on a regression with M34, Mineral Creek at Silverton for 1999. Here's the East Mancos River, model stream flow based on regression with the Mancos River at Mancos during 2019. And we have water quality samples we've collected. Mineral Creek at Burrow Bridge, we see with increasing discharge, we have decreasing copper concentrations. East Mancos River at the mouth, we have, when there's increasing discharges, we have increasing dissolved copper concentrations. These two responses of the watersheds are opposite. What does your watershed look like? And so we can continue with this analysis. Model dissolved copper concentrations are shown here, where, typical of most watersheds, snowmelt dilutes the concentrations. Whereas over here in the East Mancos, increasing discharges create increasing concentrations. This graph shows the upper and lower 90% confidence intervals, which actually I should be showing over here on these other graphs. We'll talk about this some more later. So we can continue with the modeling of dissolved copper instantaneous mass discharge. Mineral Creek, we see, despite the decreasing concentrations, we have increasing IMD during the snowmelt runoff period and increasing IMD during these rainfall events. 99 was a wet summer. For East Mancos River, we have dramatic increases in the instantaneous mass discharge, going up to 500,000 micrograms per second. And this is what I want to impress on everyone. So imagine looking at that stream section, and you're holding that water sample bottle in your hand, and you might imagine 500,000 micrograms per second going up past that stream section. This is a visualization of the real world. So aquatic toxicity can be assessed by doing these models and looking at concentrations. Can your fish survive in this concentration here during snowmelt runoff? Can fish survive in this copper concentration during runoff? Water quality standards can be established based on seasonal IMD. Where in the East Mancus there's at least 2 seasons, probably 3. But here I'm showing low flow and high flow. It is currently not that way. It's one standard for the entire year. Here's some other good ideas. Ken Lai with the USGS did regression modeling on stream flow and water quality data during 1997 and 98, and showing stream loading profiles. There's that word load. And so what's significant about this is Ken broke it out by season. A base flow, snowmelt runoff season, and a monsoon season. This loading profile starts at M2 near Red Mountain Pass, goes to M34, Mineral Creek at Silverton. You can see these loading profiles. The highest one looks like it's June. The lowest profile here is February. And the only thing I might comment here is that these points should probably have error bars on them. Ken Leib did a rigorous statistical analysis, and his errors are probably shown in those tables, yet some error bars could probably be shown here as well to represent the spread in the data. Here's another approach by Brian Kimball, doing stream tracer injection tests. From 1997 through 2000, he patched together 3 years of tracer tests using this normalized load. There's that word again. This normalized load was using the cumulative in-stream load at the end of the reach to then get a ratio of these other loads back upstream from the reach. Well, I understand some of what he's saying there, but these were all collected during 3-year periods when the flow conditions were dramatically different. And in other attempts to normalize, you would think that there's a travel time between here and the mouth of the watershed if you were to normalize to the mouth of the watershed. But the biggest problem I see with this approach is a non-conservative constituent behavior, where here we see copper. There's copper losses through this reach, likely throughout the entire watershed. And in the East Mancus, the copper pretty much disappears by the time it gets to the mouth of the watershed. So this approach would probably not work in the East Mancus due to non-conservative constituent behavior. I want to point out again that there should probably be some error bars or confidence intervals shown on these graphs. Conclusions. Instantaneous mass discharge is an effective term to express constituent mass loading in alpine streams. The term load has been used inconsistently to represent many different things. We're not expecting to change use of the term load in wastewater treatment plant design or TMDL programs for that matter. As a suggestion, be more specific Don't call it load. Describe what it really represents. Regression modeled instantaneous mass discharge on the y-axis. Stream profiles of synoptic instantaneous mass discharge. Normalized tracer dilution instantaneous mass discharge on the y-axis. And then this one's tough. The daily mean extrapolation of instantaneous values. That's a biggie. And again, error bars and confidence intervals need to be shown to represent the spread in the data. So the take-home message is you cannot calculate instantaneous mass discharge without discharge measurements. The floating orange peel method is better than nothing, where your orange peel is neutrally buoyant and goes to the centroid of the flow, and you can measure the velocity of the orange peel and multiply by the cross-sectional area of the stream. Whereas here's Dave Gray, USGS, courageously wading Cement Creek to measure discharge during snowmelt runoff. Dave's my hero.